Okay. Independent events, I like to just think about what the word independent means to me in the English language, right? Like if we're saying you're independent, you've got independence, what does that mean? Hey, you're on your own. You're all by yourself. You're taking care of things. You don't need anybody else, right? You're independent. So when we're talking about events and probability, independent events are events where they don't affect each other. They stand alone. They don't get changed by anything else. The result of one event does not affect the probability of any other events that follow. Okay, they are independent of one another. And I'm going to go ahead and also write on here that independent events, we're talking about independent and dependent events. These are when we're talking about like two or more separate events. Later in the chapter in section 10.4, we'll talk about events and we'll describe them as disjoint and overlapping. And those are when we're talking about like a single event, but there are multiple outcomes in the same event. But right now we're talking about two totally separate events. With replacement, I'm going to talk about here in just a little bit, but that's, if you ever read with replacement, that's kind of a signal that you're talking about independent events. You know, I didn't change much for dependent because we would probably argue that dependent is the opposite of independent. And so I have here that dependent events are the result of one event does affect the probability of the events that follow. And those will be without replacement. Okay, so just the same way Quinn said, independent meant you are on your own, you're taking care of things. Dependent means you rely on someone, right? You look to someone for something. Here, these events get changed by what happens before them. So they depend on what happened previously. Okay. And those are signified a lot of times with the words without replacement. You don't always get that, but that often means that. So just to kind of give an example with replacement and without replacement, if I take all of your names and I put them into a hat and I say I'm going to draw two names, and I've got two candy bars, and whosever name I draw, you get a candy bar. Okay. You know, think about in this class, what's the probability that your name gets pulled? 1 out of, looks like 20 if TJ were in here. It would be 1 out of 20 for your name. Well, if I say that after I pull a name, I'm going to put that name back in the mix, your probability doesn't change. You still got 1 out of 20, right? So those are independent events because I've done without or I've done with replacement. I keep putting it back in, I still have 20 names. But if I say, you know, I don't want to give one person 2 candy bars, so now I'm going to do it without replacement. So what's the probability that your name gets pulled on the first pick? 1 out of 20, and then I reach in and I pull Elvis. He's got a candy bar, and then I throw the name in the trash so that he doesn't get 2 of them. Your probability of getting a candy bar is now 1 out of 19. So it depended on whose name I pulled. If I pulled Elvis's name, his probability of getting his name pulled, and I throw his name in the trash is now 0. Absolutely not going to happen unless I reach into the trash can. So that's an example of the difference between with replacement and without replacement. You've got a few examples coming up here, so can you just read through them and like with your group kind of decide whether you think they're independent or dependent? Go ahead and write that down. We'll talk about them. Probably number 3 is the one your group needs to have the most conversation about.
Okay. Number 1 is true. Month is selected as
But the fate, like, whatever month or day you take is not going to be affected by what you're not doing month. If you take one day, it's still
You're not choosing a month, you're choosing a day.
I think it's the end of the month.
Yeah, it would be, right, yeah, okay, good.
It's like February.
So like it's like you're drawing the month and then after that you draw the day. So like
Yeah, but still every year has its expenses.
Right,
It's like.
Okay, let's come together and see what we say. Alright, you draw a queen, you replace the card, and then you draw another queen. Megan, what did your group say for that? Independent, awesome. What's the kind of giveaway there? You replace the card. Okay, if you replace the card, that's with replacement, which is independent events. So let's just kind of work through this probably number-wise. Some of us are better at cards than others, so we'll kind of help each other out. How many cards are in the standard deck? 52. 52, okay. What is, for the first one, this is like the probability of a queen and then a queen. What's the probability of getting the first queen? 4 out of 52. And then if I say, oh look, I got the queen of hearts, and I stick it back in the deck and shuffle it up again, now what's the probability of getting the second queen? 4 out of 52. So the probability didn't change, right? The queen was always 4 out of 52. So that's independent. Versus the second bullet, you draw a king, keep it, then draw a non-face card. What did you guys say for that? Dependent. That was pretty obvious. What's the giveaway there? You're keeping it. So that's now without replacement. Okay, so let's think about this. How many kings are in the deck of cards? 4. How many non-face cards are in the deck of cards?
You can start ace face.
What are face cards?
King,
Queen, Jack, Queen, King.
You don't.
Joker's not in the standard deck. So how many Jack, Queen, Kings are there? There's 4 each.
12.
So there's 12 face cards, which means non-face cards there are 40. Okay, 40 non-face cards. Okay, so let's say we reach it. So we're going to do the probability of a king and then a non-face card. So first of all, what's the probability that I draw a king? 4 out of 52. And like, let's say I reach in and I'm like, ooh, king of spades. Look, I got the king of spades. I'm going to keep this. What's the probability of reaching in and grabbing a non-face card? 40 out of 51. Where normally pulling a non-face card would be 40 out of 52. So because we had to reduce the total number of outcomes because I'm holding on to the king of spades, then that means that's a dependent event. Okay, are we seeing that change in probability? Okay, last one is probably the one that can be a little bit tricky. Let's hear from somebody who's willing to like make an argument for their independent or dependent. A month is selected at random. A day of the month is then selected. Rihanna, your group said?
You said dependent
Reason?
because if you like, for example, if you selected February, it had 28 days, when other months have like 30 or 31. So.
For independent, I'm not really sure what it's like, it just depends on what we're looking for. It's like the likelihood of the day being picked in the year, or like a day being picked at all. So,
Yeah, I'm picking a day in the month. Not in the year, in the month.
that would be,
Then it would be dependent. Like,
I was gonna argue for
so I can see the argument for independent. Do you want to at least just kind of like say what you guys were?
No, I was gonna argue for.
Oh, for dependent. Oh, okay, yeah.
I think you're right.
I can see where sometimes you think like, well, whatever month I pick, it doesn't make me choose a number, right? But the idea here is, depending on the month that you pick, what kinds of numbers are you allowed to choose? So I like the example of like giving different months that have different days, right? So like, if it's like probability that you pick a month and then you pick the 31st in February, that's going to have a different probability based on the month. Okay, so that would be a dependent event. Excellent. Okay, now let's get into the formulas. I think I got the first part down for you, and you need to fill in the actual formula part. Go ahead and copy that down. Now, on the paper, it says the probability of A and B. And I just put underneath it in quotes, I put then. Like, and then. We're going to see other probabilities of A and B later on in the chapter, just to like mess with you, right? And at that point, later in the chapter, and is going to mean at the same time. But what we mean when we're talking about independent and dependent is, remember, we have two or more separate events. So when we say the probability of A and B occurring, we're talking about this and then the other thing. So there's two separate events there. Well, if they're independent, their probabilities are totally by themselves, doesn't depend on anything, all alone. So you just take the probability of A and you multiply it by the probability of B and you're done. If they are dependent, you're going to see some different notation there for your second probability. Because remember, if you have dependent events, the probability of one depends on what happened previously. So that's that notation. Probability of B, it's a vertical line, and then it has an A.
So is that like times?
This is times right there. This is just a notation. I'm going to write about it here right now. Okay, what that notation means is it's a probability of event B given that event A has already happened. So when you're thinking about that, think about those examples we just ran through. The second one was the probability of getting a king and then a non-face card if I keep the face card, or if I keep the king. So when we did that probability, the probability of the king didn't change. It was just 4 out of 52. But when we did the second probability, the probability of getting a non-face card, if I'm holding on to the king, that probability now depends on the fact that there are one less card in the deck. So it's 40 out of 51 instead of 40 out of 52. So the key word in that, and this is how you'll often hear it read, is just, I would say it's the probability of B given A. And it just means, I know A is true. So that's a given to me. If A is true, what's the probability of B? And that's going to show up again later. This probability, on the back side, we're going to be talking about conditional probabilities. This is called the conditional probability. It has a condition that A happened. Okay? And it depends on it. Okay, so we've got some examples. I'm actually just going to let you and your groups take a few minutes to try to read through and come up with a plan, like what you want to do to calculate the probabilities. Oh, I should say this before I let you just like totally loose on this. I want you to write it down somewhere today. I don't have a spot for it. But this will come in handy later in the chapter when we have other words. Okay, I'm going to put and, meaning and then, means multiply. Right? So like this notation with the B given A doesn't mean anything mathematically, it's just a probability. But in both formulas, you're just multiplying two probabilities together. And if there were like 3 separate events, then you would multiply 3 events together, 3 probabilities together. So you should be focused today on that multiply. Okay, now read 1 and 2 with your groups and see if you can come up with some solutions.
First event, and that there's $500. Yeah, so the first time that you're gonna get on your dollar bill is 5 out of 25. Like one, so that's on. No, 1/5 is helpful for you. You have, so now we have to do it. So now there's 24 and a half. And I think now it's supposed to be 30. And then so you can okay, so the probability would be 1%. He would be 1%.
No.
Okay, so the 3.5 is what?
I said that.
I didn't know.
You don't even know her name. Oh, like,
Yeah, I
yeah.
I didn't look at it.
It was one because the first and second will are
1/5 is the probability.
their silent roughly that otherwise they would both be within.
Okay, so we're using
Oh, right.
Okay, let's come together and see where we're at. Okay, we got a bag. It contains 20 $1 bills and 5 $100 bills. I'd like to have that bag. You randomly draw a bill from the bag, you set it aside, and then you randomly draw another bill from the bag. Find the probability that the first and the second bill is $100. So I like to use probability notation. I'm going to write it like this, just like as a shortcut, and I kind of can keep track of what I'm trying to do. I want the probability of 100 and then 100, right? Dollar bill. You can write it in your own words however you want, but I do like to use probability notation. So I would encourage you to start trying to write your own probability notation. All right, well, are these events independent or dependent? Dependent. The giveaway there is set it aside, right? Okay, that means without replacement. So this is going to be a dependent event, which means when we find the probability of this second $100 bill, we have to consider the fact that we had already pulled a $100 bill before. We're going to assume that A happens. So let's just focus on the first $100 bill. What's the probability you reach in that bag and you grab a $100 bill? Lexi? 5 out of 25. I heard some people reduce that 1/5. Either one is fine. So I'll just do 5 out of 25. That's fine. And then suppose, okay, yay, I got a Benjamin Franklin, right? I got a $100 bill. This makes me feel good. I'll put it in my pocket. And now I'm going to reach into the bag again. What's the probability that the next bill I draw is also a $100 bill? 4 out of 24. So you could type that in your calculator. If you did 1/5, and then this one would be 1/4, right? No, 1/6. Sorry. This one would be 1/6. Okay. You could get 1/30th, or like if I was working off of the 5 out of 25 and 4 out of 24, I just type that in my calculator. Like I'm not gonna mess around with simplifying a fraction. I'll just do 5 divided by 25 times 4 divided by 24. Oh, that's 0.033. You could also say 3.3%. But either one of those. So the chances aren't great that I get $200 bills, but that would be awesome if I did. Okay, let's look at the next example. Find the probability of drawing 2 cards from the standard 52 card deck and selecting a heart and a red card. So can we just talk about what's in the deck? What do you know about hearts?
13. They're cool as heck.
There's 13. They're one of the suits, and there are 4 suits in the deck. So there's 13 hearts, 13 diamonds, 13 spades, 13 clubs. What do you know about red cards?
3.6.
There's half of the deck. Half of the deck is red and half the deck is black. Okay, so we have 2 questions here. First one, find the probability of a heart and then a red card with replacement. So part A means these are independent events. When they're independent events, you don't have to stop and think about the second probability. You just figure their individual probabilities. So what is the probability of pulling a heart? 13 out of 52, or you could say 1 out of 4, either one of those. What's the probability of pulling a red card? 1/2, because it's half the deck, or 26 out of 52, however you choose to write it, right? And so this would be like 1/8, or it's like 0.125. There's my probability. Okay, in part B, I want to do the same situation, probability of a heart and then a red card, except this time I'm going to do it without replacement. So that means my events are now dependent. Okay. When you have dependent events, it's not the first event that you have to worry about, it's the following events. So the first one, probability of pulling a heart, is still 1/4, right? Now, suppose I reach into the deck and I do pull a heart. Let's say I pull the 8 of hearts. And I'm like, woo, a heart. Okay, I'm going to keep it. What's the probability when I reach into the deck now that I get a red card? Fish? 25 out of 51. Where did your 25 come from?
Because the heart is a red card. You took it out.
Excellent. So you got to think about on this one, the heart is a red card. So now there's 1 less red card, and there's 1 less card in the deck. Sometimes you change the numerator and the denominator. Sometimes, like with my names example, we just change the denominator. Okay, and on this one, I'd probably just multiply across. So that's going to be 25 times 4 times, or divided by 4 times 51. What is that? 204. So that comes out to be like 0.123. So you actually have a little bit less probability of making that happen if you don't replace. That makes sense. Okay. But it's pretty close because you still have a lot of cards, right? Okay. Now, on the back side, we got to talk about conditional probability. Conditional probability is that extra probability, that weird probability in dependent events. The probability B given A. the same way I think about like independent and dependent just as words in the English language, I think about conditional probability. You know, it's probability on a condition. And the condition is that the first event already occurred, and that changes the probability of my second event. So the probability that event B will occur given that event A has already occurred. This only happens when we have dependent events because we're changing the probability of one based on what has already happened. And that notation is that same notation we saw earlier, the probability of B given A. Okay, so that's your conditional probability. Now, I have a new formula here, but like let's just be clear, it's the same formula I gave you on the other side of the paper. I just rearranged some things, right? So if you look at your formula on the other side of the paper, you've got dependent events. That's the probability of A and B is equal to the probability of event A times the probability of event B given that A has already occurred. And now we're just solving for this probability. So if this probability is being multiplied by the probability of A, we have to divide by the probability of A. Okay. So if I divide by the probability of A, then I get conditional probability. So you can know two formulas or you can know one formula and always kind of like solve backwards for one. Okay, so they're essentially the same formula. Now, conditional probability can work differently in different scenarios. So we're going to look at this example with the two-way table, which that's tomorrow. We're going to be doing a lot of work with tables. Okay. A computer lab has 10 computers. Notice that's the total right down here in the bottom right of the table, right? 10 total computers. Some of them have CD drives, some of them have DVD drives, some of them are new, some of them are used. A student picks a computer at random. So how many computers are they picking here? This is one. So this is not necessarily independent and dependent. It's picking one computer. Use the table to find each probability. Okay. What's the probability that I pick a computer, I go into the computer lab, I sit down, and it is new? 7 out of 10. There are 7 new computers to choose from. There are 10 computers in the lab. So it would just be 7 out of 10. That's basic probability. Okay, what's the probability I walk into the lab and I just sit down at any old computer and I sit at one with a CD drive? 6 out of 10. Okay, 6 of them have CD drives. There are 10 computers, so that would be what? 3 out of 5. Now, on this one, I say, what's the probability that's new and it has a CD drive? Because we're only picking one computer, it must mean like that computer has both things at the same time, right? So this is at the same time, not necessarily multiplied. That would be what? 4 out of 10. There are 4 new computers with CD drives. Okay, so that'd be 4 out of 10 or 2/5. Okay, and now this is where we get into conditional probability on a table. What's the probability that the computer is new given that it has a CD drive? So this CD is your given, right? You know it has a CD drive. How many computers have a CD drive?
6.
Oh, 6.
6 computers have a CD drive. So given that it has a CD drive, we've now narrowed it down from 10 computers to 6. Because it's given to us. What's the probability that it's new now? 4 out of 6. Okay. So the given might change your total outcomes. If I know it has a CD drive, I'm not looking at the DVD column at all. So I'm only looking at these 6. Okay. Now let's see if we can apply that to the next problem. A quality control inspector checks for defective parts. The table below shows the results of the inspector's work. So some defective parts will pass. Looks like most defective parts will fail. Most non-defective parts will pass, which makes sense. But there will be some non-defective parts that do fail the test. So find the probability that a defective part passes. What are we looking at there?
5 out of 29.
Okay, tell us how you got that, Quinn.
Okay, so the total of pass, fail, defective is 29, and pass is 5 out of 29.
Okay. Find the probability that a defective part, that's your given. You know it's defective. So do I care about any of the numbers for non-defective? No. So this is saying find the probability that the part will pass given that it's defective. And Quinn was right, 5 out of 29. So see if you can take a quick stab at part B. Find the probability that a non-defective part passes. You want to know the probability of a pass? What do you know about the part? Given that it's non-defective, so we're looking only at the non-defectives, which is 217, and that's going to be 208 divided by 217. Okay, so you really have to read your probability statements very carefully. If the probability statement and you're looking at a two-way table problem is giving you a particular characteristic, then you need to look only at that column or row. All right, we've got one more. We got 2 minutes, then we can go.
We have a bus change. Bus number 15B will change to 04B. Again, that 15B is changing to 04B.
Okay, just to kind of get you, because there will be some problems similar to this on the homework, so kind of give you an idea of what you can do here. Okay, first I like to use probability notation and put into words what I know. Probability of pants is 0.75. That's the probability they buy pants. The probability that my customer buys pants and a belt is 0.2. So I could treat pants like event A. Pants and a belt would be probability of A and B. Okay? And then I want the probability that a customer who buys pants, so it's given to me that they buy pants, also buys a belt. So that would be the probability of B given A. And we know from the formula for probability of B given A, take the probability of the two of them together and divide by the probability of A. So just to kind of give you an idea of where you would look at, what you might set up for your homework. You could also set that up as like the probability of A and B, 0.2, is equal to 0.75 times the probability of B given A. Okay? You have a homework on your gold sheet.